So we continue our lectures, and today we will consider Brownian motion as martingale. So we considered it as a Markov process of the previous lecture, but Brownian motion belongs to another very important class of random processes, and this property is very important in the construction of the integral with respect to Brownian motion. So we are starting to consider this property now. So first, let us give the precise definition of martingale. So this is definition. So I will consider a real valued process x that defines on the real on the half line. T is greater than 0, and it is called martingale. And again, we need to specify filtration, and I write here with respect to filtration. So I will consider some filtration ft, where t is greater than 0, if following properties hold. First, we need to assume that process x is adapted with respect to this filtration ft. So recall, what does it mean? So this means that for each t greater than 0, the value of process at time t is measurable with respect to sigma algebra at time t. So we know the so we have such measurability. The next assumption that we need is that this process has final expectations. So we assume that for each t, the expectation is less than infinity for each t greater than 0. And third, and the most important assumption is that for each 2 points of time s and t, if I consider the expectation of the value of the process at time t, conditioning on sigma algebra at point s, then I will get just value of process at time s. So this property says us that the best estimation of the process at time t, when we know information up to time s, is just a value of process at time s. So this is the definition of martingale. And now let us consider example. We will consider several examples that are important, and they are martingales that formed from Brownian motion. And the first example, as I told, a Brownian motion itself a martingale. So let's check it, and I formulate that if I have a Brownian motion, we denote it by BT. So this is standard Brownian motion. And I consider filtration as before Ft. I defined as sigma algebra generalized by sigma algebra generated by all values of a Brownian motion up to time t. This is my filtration. Of course, here t is arbitrary. So first, two properties of the definition, we will just say a couple of words. So we know that from such a definition, BT is FT measurable. Yes, because the sigma algebra FT has the random value here b at time t. So this is obvious. The next expectation, of course, we know the distribution of Brownian motion at time t, and it is, of course, finite. So this is easy. And the third property that we need to check that conditional expectation of Brownian motion at time t with respect to sigma field, with respect to sigma algebra Fs, we need to check that it is equal to Brownian motion at time s. So again, we know that Brownian motion has independent increments. So our approach as before, we need to add and subscribe the value at time s here. And now I have the measurable part. This is b from s, as we said in the first property, is measurable with respect to sigma algebra Fs. So I write here b from s. And what I have inside expectation, this is b from t minus b from s, expectation with respect to sigma algebra Fs. And now I use independent of increments. So what I use, let me write here, since b from t minus b from s is independent of Fs, then the conditional expectation becomes unconditional. Yes, we know that if I consider conditional expectation of value that is not depend on sigma algebra, this is just expectation. And we know that expectation of Brownian motion is equal to 0. Yes. So we have such explanation of what I am writing now. So this is just, we have value b from s. So yes, this property satisfied for Brownian motion. Okay, so let us consider another example. What functions of Brownian motion will be martingales again? What if I consider a square of Brownian motion? Of course, it is not a martingale. You can check it because you will not have here equality. So I need to subscribe something. And let us check that if I write here minus t, then such a process, so this is a process, will be a martingale. Martingale. When I do not say with respect what sigma field, I mean that I consider sigma field that's generated by this process. So let us check, I believe, third property because first two are obvious. So let's start from considering the conditional expectation. Again, we need to check that this conditional expectation is equal to value at time s. And as before, since I can work with increments of Brownian motion, I just write here plus minus b from s to the square minus t. So let me open the brackets here, and this is what we have. B from t to the square plus b from just a second. I will consider b from t minus b from s. So this minus, yes, I consider this. Then plus b from s to the square and minus 2b from s, b from t minus b from s, and this last t with respect to sigma field s. So now I will not explain in detail, but I will just say it. So we have this part is independent of fs. So we have just here unconditional expectation. Yes, so I write for the first one is unconditional expectation to the square. Then the next, this one is measurable with respect to fs. So for this term, I write just without expectation b squared of s. And here, the one part is measurable. So this measurable, and this part is independent of fs. So measurable part I take out of the expectation, and for the second I just write unconditional expectation. Okay, and minus t. So now I have no any conditional expectation. I have just expectation, and we know that the this is the variance of increments. We know that bt minus bs has Gaussian distribution with zero mean and variance t minus s. So I write this as for first term. B square from s I write as it was, and this here the expectation is equal to 0. So this is just 0 and the last minus t. So this is what we want. This is the value of b square of s minus s. So this process is martingale as we stated. Okay, And third, but also very important example, and we will use it in the second part of our lecture. We will see that we can make some very important conclusion from this process. So another function of Brownian motion, that is martingale again. So as before, B from T is the Brownian motion, and I will define such a process. I will denote it by Z from T. That is equal to exponent to the power sigma B from T minus 1 over 2 sigma square T. So this is the process with respect to time T. And here sigma, some number, sigma greater than 0. Okay, so let us check that this process is, and what is martingale. Okay, the first property that this Z from T is measurable with respect to Ft is obvious. Then we need to check that expectation of Zt is finite. And this is true because we know that this is, we know the expectation of exponent of Brownian motion, so this is finite. Yes, you can recall moment generating function of Brownian motion, and you can remember that this is finite. Okay, so the third very important the properties that we need to check, that conditional expectation of Z from T with respect to S again will be the value of Z of S. So, and as before, we do the same thing. I will write here B from T minus B from S and plus B from S. So this is very easy to remember and it is not hard. Okay, so, and I consider conditional expectation here. So what I have, first you can know that we have non-random part. I can write it here, exponent to the power minus 1 over 2 sigma squared T. And here, what is remaining, this. And also I can write here measurable part. Again, this is measurable with respect to sigma field Fs. And I will write it before the expectation here as measurable part B from S. Yes, so this is exponent of this. And here, what will remain here, this increment of Brownian motion. And I will not write conditional expectation, yes, if I write here, but this part is independent of sigma field, so I have just unconditional expectation of this. Okay, and now we just need to recall what is the expectation of e to the power some Gaussian random variable. So this is sigma B from S, and this is just e to the power 1 over 2 sigma square T minus S. Yes. So this is the moment generating function of Gaussian random variable. Okay, so put all this together. We have e to the power sigma from P from S, and here minus this part and this part is cancelled. So I have only 1/2 sigma square S. Okay, so this is the value of Z from S. So we have such three very important examples, and you will see that we will come back to them during our lectures. But now let us consider some important properties that makes the martingales so useful processes in the theory of stochastic differential equation. So let us consider some properties of martingales. So this is for general martingales, not only for Brownian motion. So let's think about such property. The third property of definition of martingales says us that expectation of b from t with respect to this condition to sigma field fs is equal, or this is for any martingale, so I will write here s. We have such a property. If I write here the expectation of the right part and left, I will have such a property of martingales that x from t is equal to expectation of x from s, and since I can take s less than t, this is equal to expectation of x from 0. Yes, so this is true for all t. Yes. But now we are going to consider not the deterministic moment of time, but a random moment of time. So I will write a question: is it true for random moment of time? And of course, we will find some assumptions under which this is true. But first, I would like to start from an example when it is not true. So let us consider an example. If I consider some number m, which is, for example, greater than 0, and I consider such a random time, tau m, which is equal to infimum over all t's, such, let me take m strictly than greater than 0, such that, for example, for Brownian motion, at t is equal to m. So this is just the first time when Brownian motion come to some level m. So if I have some trajectory, this is the first time when m b hits level. So this is tau. And so what is the question now? If I consider Brownian motion at moment time tau m, And I ask, is the expectation of this value is equal to expectation of Brownian motion at 0? Is it true? Of course, it is not true, because Brownian motion at this moment of time is equal to m. Yes, if we have that this is that moment that b from m is equal to. So, of course, then the expectation b from tau m is equal to m, and it is not equal to 0, because this is here. So we see here that we should be very so we need to get some assumptions on random moments or at some process to be sure that this property holds. This one when t is random moment. So let us start to formulate the assumption on random moments of time. First, we will consider not arbitrary moments of time, but so-called stopping time. And for this, I give the definition. A random variable t. I will assume that it is from 0 infinity or infinity itself. So it can can take values equal to infinity. So this random variable is called stopping time. And again, I need to specify filtration with respect to some filtration at t. If I have such a property that random event that t is less or equal to small belongs to sigma field ft for all t greater than 0. So what does this property say? That this means that every stopping time we can say that t is less or equal to t. So for every such event, we can say that if it happens with information ft. So let us give some examples of stopping time for Brownian motion. For example, let us check that the first heating time tau m less than t belongs to ft. Let us check, and I will recall here that tau m as before infimum of t greater than 0 such that b from t is equal to m. And ft is sigma field generated by Brownian motion. So this is the question. So how we can check this? So tau m is less than t. Let me draw a picture. Here we have some level m, and Brownian motion first hit time m at this. And I know that tau m is less than t. We can consider the not this event, but complement for this event. So I say that this belongs to ft. We know that if and only if the complement m tau less greater than t belongs to ft. Yes, this is just a property of sigma field. And now the event that tau m is greater than t, this means that if I take here some time t, and I know that tau m is greater than t, this means for this events tau m just equal that for each s less than t, Brownian motion is less than m. Yes, so this is event that based on values of Brownian motion up to time t. So by definition of sigma field ft, this is belongs to ft. So from this we can see that moment time tau m is a stopping time. Okay, so we have such a very important example of stopping time, and let us continue our investigation of how when we can substitute to the quality that expectation of process at some stopping time equal to expectation from process at 0. So, and to this end, we first prove such an easy lemma. I'm sorry, not now. For simplicity, to consider more simple case. For simple case, just to understand the idea, we consider martingales with respect with this discrete time. Discrete time. So it turns out that it is much more easy to work with discrete time martingales. So the definition for discrete time martingales are the same as for continuous time, but I have here the indexes of time, just natural numbers. So we have n here, and I have a sequence of sigma fields fn here also. Okay, so this is martingale. I recall that all properties in definition for continuous time martingale hold. Just we have here discrete moments of time. So let me write, for example, the third property of martingale that we have that for each m less than n, we have that. Sorry. We have that conditional expectation for process at time n with respect to f. M is equal to the value of process x at time m. So this is the case very similar to definition that we gave. And for, so this is Martingale, I will write. And as in the definition of stopping time, now time is discrete. So the random variable t that is equal to 0, 1, 2, and so on, and infinity, is stopping time for sigma field fn if, as before, I have that the event t is less or equal to n belongs to n. So this is very this is the definition is the same as for continuous time. Okay, so now let us formulate the lemma for discrete time martingales, and then we will be able to generalize it for continuous time. So lemma, if I have x and with respect to sigma field f, and this is martingale, and t is stopping time. For the same sigma field f, and for the same filtration, then such a process, let me denote it by x n, and here upper index t, that is defined as x at the moment n minimum t. Such a process and greater than 0 is martingale again. Here I use notation, and I will use it in the future. This n such symbol t, just the minimum between n and t. So let us check that such this process called x and t, called stopped process. Why is it so? Because if I have some, for example, I have process, and here are some random value t, and my process somehow it is with discrete time now. I have such a value, and when before random variable t, I have the just value x n, but after this I have just value xt. So I can just, the process stopped here and remains at this value for all future. So this is trajectory of x and t. And for example, non-stopped process was something like that, something like this. Okay, so this is just x. And so this is the picture of stopped process. So now let us check that this stopped process is martingale. This is for proof. What we need to check is the third property of definition of martingale. So I will check that this n minimum t with respect to, I will write here n plus 1 minimum t with respect to sigma field, sigma algebra Fn. So I will now take all values of random variable t. So I just write the sum of k from 0 to infinity. The same what I have here, the expectation of the same value, minimum t. And here I write indicator of the event that t is equal to k. Yes, I just take all possible values for random variable t. So now what I can do next, I know that this minimum is equal to n plus 1 for values for those k when k is less than n. So when I have the value k from 0 to n, then t is less than n, and of course I write here xk, indicator that t is equal to k. Yes, so t is less than n plus 1 for this case with respect to fn, and for k from n plus 1 to infinity, what value here we use? T is equal to k, and it is greater than n plus 1, so I write here x n plus 1, indicator that t is equal to k with respect to that. So now what do I have here? We assumed that xk is martingale, x is martingale. So the value x k is fk measurable by definition. And since I recall f is the filtration, and before we defined that it has property that fk is a part of fn for k less than n. Yes. So from this follows that xk is fn measurable also for k less or equal than n. So here I have measurable random variable with respect to fn. Also t is stopping time. So event t is equal to k we can you can write it as, for example, t less or equal than k without t is t is less than k. And this is this event belongs to sigma field Fk, and it is sub sigma field of Fn. So also this event t is equal to k is Fn measurable for k less than n, less or equal to n. Okay, so with this what we have here, that and this random variable also is Fn measurable. So in the first summand, I will continue here. So this is just explanation for what I'm writing next. This is explanation. And now I write in the first sum, we have measurable random variables with respect to sigma field. So this is just this random variables itself. Yes. So this is it tau t is equal to k. And now in the next summand, I have here sum, and I will write this sum. I will write it here. So I will sum the indicators when t is equal to k, and this sum is equal to expectation of xt, and here I write summation of k from n plus 1 to infinity, indicate that t is equal to k with respect to filtration f n. So here I just write the first summand as it is, t is equal to k, and here I will write this summand sum. This is just t, and here indicate that t is greater or equal than n plus 1 with respect to fn. And I'm sorry. I have here index n plus 1. I'm sorry, it's important. N plus 1, n plus 1. Now this indicator is Fn measurable. Yes, why is it so? Because event t that is greater than n plus 1, I can take the complement of this event. This is t is less than n plus 1, and since t is discrete, this is just event t less than n, and it belongs to Fn. So I can put this indicator inside of conditional expectation and continue my equality. And this is equal to k from 0 to n of x. K indicated that t is equal to k, and here plus what I have indicated that t is greater or equal than n plus 1. And I have here conditional expectation xn plus 1 with condition to fn. And I assume that xn is martingale, and this conditional expectation just equal to xn plus 1. So you can see that this is exactly, oh, I'm sorry, xn. So, and this is equal to just xn minimum t. Yes, because when n less than t, we have just first summand, and here we have just x and when t less than n, yes, we have just x t. But when n is greater than t, we have this part. And this is it. So we checked that where we started. We started from conditional expectation from xn plus 1 minimum t, and we proved that it is equal to xn minimum t. So from this follows that xn minimum t, such a process with discrete time, is martingale. Okay, and now we can formulate the theorem, so-called theorem. This is called optional stopping theorem. So the idea, what we have now, we have that, I will write here, what we have proved is that the stopped process is a martingale, so we can write this x 0, yes, we know this. And now the main idea to pass to the limit. So when we can pass to the limit, when n tends to infinity, yes, when we get the limit, we will get just expectation of x at random moment t. So this gives us the idea what conditions for t we need to assume. So as before, the theorem assumes that t is a stopped time. This is important property. Stopped time. And x is martingale. And x and is martingale. Then the first statement xt is integrable, and equality expectation x at moment t is equal to x at 0 holds. If so, we need to condition if one of condition hold. So this is true when if t is bounded time. So this means that exists such a number and that t is less than n, almost sure. And another condition that is the process x and t is dominated by integrable random value, of z, for example. So this means that x and t less than z for all n 0 almost. So now this the proof of this theorem is very easy. We just need to what we have. We proved that, as I said, n minimum t is martingale, so this expectation is equal to expectation of x0. So now we need to uh, in the first case, we can take n is greater than this number n. Then n minimum t is just equal to t, yes, because we know that t is less than n capital. So in this case, the expectation of n minimum t is equal to xo. Expectation of x equal to expectation of x at time t and is equal to expectation of x0. This is done. The second part, we need to get to the limit in this equation and limit x n minimum t when n goes to infinity is equal to expectation of limit to n to the infinity x n minimum t by dominated convergence theorem. Dominated convergence theorem. Because we assume that x is bounded by integrable random variable. And so from this we have that expectation of limit x n minimum t is equal just x at time t, because n here we make larger and larger, so we have the equality. So this theorem can be generalized for continuous time martingale, and assumption are the same. So I will not reformulate it, so you can use this theorem for continuous time martingale. Now I would like to, if I have some about 10 minutes, I would like to show you how we can use this theorem to investigate properties of first time when Brownian motion hits some level. So this is application of the theory that we investigated. And as before, I fix some m that is greater than 0. And for Brownian motion, I consider first time when Brownian motion hits level m. So, and now recall the process that we considered on the beginning of the lecture, that of t. So I recall that this is exponent to the power sigma b from t minus 1 over 2 sigma squared t. And we prove that this is martingale. Now, using that, I will consider time t minimum tau m. And I use that we proved that stopped process is martingale again. This is martingale. So we prove this, yes. You can use optional stopping theorem for this bounded random time. Okay, and what we can say about this when we know that this is martingale? Of course, what we have z at 0, we know that it is equal to 1. Yes, if you substitute here t is equal to 0, you have exponent to the power 0, and this is equal to 1. And by our statement, we know that it is also equal to z at tau m, and it is so we know. Now I would like to pass to the limit. Limit when t goes to infinity. So actually we do not know, yes, nothing about moment time tau m. So we cannot apply some dominated theorem for easy, but we can consider some cases. So first consider case, first case when tau is equal to then tau m is less than infinity. So in this case, I will consider that z t minimum tau m. I will write that this is exponent. I will write two exponents. This is sigma of b at t minimum tau m, and it multiplied by exponent minus 1 over 2 sigma squared t minimum tau m. So when this holds, so when I assume that tau m is less than infinity, what I can say about limits? This will tend when t is goes to infinity. At some moment t will be larger than tm, so this is just this limit sigma from b from tau m. And this part is goes to also the same. T will be larger than tau m at some moment, and this is minus 1 over 2 sigma squared tau m. Okay, so we have such limit just in this case. Now when tau m is equal to infinity, so we do not know tau m is finite or not. Yes. So in this case, z from tau minimum tau m, again I will write here that this is expectation of sigma b from t minimum tau m multiplied by exponent minus 1 over 2 sigma squared t minimum tau m. So now when I will tends t to infinity, I do not know if I have here some limit, but here I know that tau m is infinite, so here I have just exponent 1 over 2 sigma squared t, and it tends to 0 when t tends to infinity. Now let us consider this first exponent itself. And what I want to say, I want to find that this exponent is bounded. Why is it so? Because for in this case, what tau m is equal to infinity, t minimum tau m is equal t, of course, yes, for all t greater than 0. And then okay, and t minimum tau m, of course, less than tau m. But tau m is the first time when Brownian motion hits the level m. So from this follows that b from t minimum tau m is less than m. Yes, because we know if some moment time is less than first hitting time, here some tau m, here level m, then before tau m, we do not hit level m. And if tau m is infinity, this means that Brownian motion does not pass through this value m. So we know that in this case, we have such upper bound. So I can make conclusion that exponent sigma b from t minimum tau m is less than exponent to, I will write here, sigma m. Yes, so this is bounded. I will come back here and I write here. So we do not know the limit, but it is bounded. And we know that if I have some bounded value and I multiply it by a sequence that converges to 0, then all this product converges to 0 as well. Yes, we know. Now let us put together all the spot, and what do we have here? I can write that our z from t minimum tau m is equal to, indicate that tau m is less than infinity, z minimum tau m, and plus indicate that tau m is equal to infinity, z t minimum tau m. And now I want to pass to the limit when t converges to infinity. I will write it here. T converges to infinity, and this is equal to limit t converges to infinity. And I proved that what? That this is equal to, indicate this part is the first part when we have here tau less than infinity. What do we have here? Let us recall. You have it. So you have two parts here. So this is equal to exponent sigma square b at moment tau m minus 1/2 sigma square tau m. And The second summand is tends to 0, as we say, yes? So 0 multiplied by bounded random variables 0. And now I want to substitute here. We know that Brownian motion at this moment tau m is equal to m. So I write this expectation, exponent, I'm sorry, just m plus minus 1 over 2 sigma square tau. And okay, I have such a limit. And we can see that this is a bounded random variable. Yes, because we have this bound exponent or sigma m. I will write here. Exponent sigma m. So we can use dominated convergence theorem. By dominated theorem, we can get, what do we have? I have that 1 is equal to z from 0, and I would like to pass to the limit when t goes to infinity. Expectation of that t minimum tau m. And by dominated convergence theorem, I can put limit here. So this is just expectation of this part, what I have here. So I just write this exponent of sigma m minus 1 over 2 sigma squared tau. Okay, and from this, from this follows that we have such a formula for moment tau m. I can multiply right hand side and left hand side by exponent to the power minus sigma m, and we get that this is equal exponent to the power minus sigma m. Okay, so you can recognize here that we obtain Laplace transform for random variable. So how to get this? If I denote by alpha this value 1 over 2 sigma squared, then we get Laplace transform for random variables tau m, e to the power minus alpha tau m. This is equal, you can check that we can write here minus m to the power square root of 2 sigma. So this is for m greater than 0. Okay, and from this we can get, so this is such a formula. And from this we can immediately get such a good property that when we take the limit with respect to alpha that is tends to 0 of this expectation, again we have oh, I'm sorry, here not sigma, here alpha. Then this is equal to limit alpha tends to 0. Oh, I'm sorry, not this. I would like to find the first moment of tau m. And to find the first moment of tau m, we differentiate d for d alpha e minus alpha tau m. This is equal, just you can differentiate under the sign of expectation. So this is equal tau m e to the power minus alpha tau m with sign minus. And this is equal to m divided by square root 2 alpha with sign minus, of course, e to the power minus m 2 alpha. Yes. So from this, now I pass to the limit when alpha goes to 0. This expectation tau m e to the power minus alpha tau m. From one hand side, we can write here when alpha goes to 0, we just take the expectation of tau m. Yes, but using this equality that we proved, we can see that this is equal to limit when alpha goes to 0, m to the e minus m square root 2 alpha, and this is equal to infinity. So we conclude that expectation of tau m is equal to infinity. So what conclusion we can make from this? That's Brownian motion hit the boundary, but with this such a moment of time with infinite expectation. Okay, so but do this moment of time is finite? Let us again consider this equality. This equality where I'm sorry, this one, if I consider. So let me, I will do the last step. I will take this value. So this is just the limit when zt is goes to infinity. So on the other side, on the other hand, we have that this we obtain that this was the limit when was limit when t is goes to infinity expectation. I just recall you have it in your notes. So we had such or just here and here I need to write expectation here also. Here I would like to write expectation. So now I would like to pass to the limit, and I know that this is equal to 1 always. Now in this equality, as I say that we have that such an expectation tau m is equal to exponent sigma minus 1 over 2 sigma squared tau m is just equal exponent sigma m minus. Now let me pass to the limit when sigma goes to 0. I will use monotone convergence theorem, And this gets us what? When sigma goes to 0, this exponent goes to this exponent will goes to 1. Yes, because we have here 0. So this is tau m less than exponent minus 2 sigma squared tau m. And this is equal just probability that tau m less than infinity. And this value I will write from the other hand. We have equality, so this is limit when sigma goes to infinity, 0 when exponent minus sigma m, and this is equal to 1. So from this we can make conclusion that moment tau m is finite with probability. So we obtain such a true property of moment of first hitting time of level m, and we have such a true property that from the one hand side it is finite with probability 1, but from other hand it has infinite expectation. So this is such a good example when you have random variable that is finite but with infinite expectation. So I think that this is all for today's lecture. We have seen that how we can use Martingale property to investigate such a property of trajectory of a Brownian motion. Yes, so on the picture you can imagine that with probability 1 you will hit level, for example, level 1. Brownian motion will hit this level, but this tau m can be so large that its expectation is equal to infinity. So this is it for today's lecture, and if you have questions, please you can ask. Okay, if you have no questions, then thank you for your attention, and see you next time on Monday at the same time.